Today we're going to talk about quantifying fluid flow. So far we have talked about fluid in a tank and static, maybe pressure in a fluid that's sitting there, maybe pressure at a depth in a fluid, but fluid is not moving, it's static. So those things are good building blocks for fluids, but we want to also study what happens to fluids when they move. For instance, when the blood is flowing through the veins, or the water is going through the pipes, or the oil is going through the pipes. So our air is flowing through the ducts. So when a fluid is flowing, we want to be able to understand and quantify it, talk about the pressure that we'll see. You'll see the formula for pressure is a little bit different than the formula for pressure that we had in a fluid at certain depth. So you have to be careful when you're looking at fluid, whether fluid is flowing or not flowing. The first business of fluid flow is to be able to quantify how fast the fluid is flowing, how much fluid is flowing. Okay, so let's see. So this is a kitchen faucet, and you can see everything flowing. So we want to know at what rate this is flowing, and to do that we are going to introduce some ideas. So we're back to the regular place. Okay, so here is a say there's a pipe, and we're just going to draw it horizontal. So maybe it has uniform cross section. So this is the cross section area of the pipe. So this area is called cross section area. And fluid is flowing through this, right? So if you were to collect all this fluid in a bucket, and you say how much volume this flow has resulted in certain amount of time. So the volume. So we'll have a volume over some time is a very important measure of the fluid flow, and we call it volume rate of flow, or just a rate of flow sometimes. So this is for instance, this may be a meter cube. There's a lot of fluid, okay, over seconds. This would be a very big unit. So usually you have a liter per minute for the volume and time for minutes, but this would be the SI units. If we need a name for this, right? So we'll just call it a Q, and this is going to be volume per time. Okay, so that looks like a good thing to have. How much volume, how much fluid is flowing, the total fluid that's flowing. But if you look inside the pipe, and we will see that the very center of the pipe has a much faster flow than the next, and right at the pipe it doesn't flow very much. So the speed of the flow is kind of varies across pipe, and that becomes very complicated, right? But I want to actually say no, I will just want to capture average speed. Okay, so we say I want to assign some kind of average speed, not all of the different speeds. Just say everything is going with the same speed. all of this water flowing at the same speed. And we'll call that speed V. And so that's the flow speed. So this is called flow speed. And this is just I imagine if I were to put some kind of, say, blue ink over here, and this is not how real fluids flow, but say this thing, and it's flowing at V, it will end up over here after 1 second, right? So this is the distance it would have traveled in 1 unit of time. So this will be meter per second. So you can see that there is in 1 second, this much flows, right? So this much volume will flow in 1 second. So what's the volume? If the area of cross section is, say, letter A represents area of cross sections. If this is area A and it is flown in 1 second, it has flown V. V is a meter per second, so in 1 second it will flow V. So if you're looking at in time delta T, so go V times delta T. But in 1 second, because we're looking for 1 second per unit time. So this is the volume. That's how much it would have come into my collection here, right? So another way to say Q should equal to this A times V. So this is the same thing, volume. So this is the same thing as volume per unit time. This is a very important result for us that we'll see. There are many uses of this in just a second. Okay, so we just defined the definition of volume rate of flow, and normally use the letter Q for it. This is the area of cross section. And this is some average speed, also called flow speed. Okay? I want to show you one important implication of this for incompressible fluids. Like water. Water is a very incompressible fluid. By incompressible, I mean that when I put pressure on it outside, when I compress on the fluid, the volume changes very little, and we can neglect the change in the volume for normal range of pressures. Okay, so if it is incompressible, then consider this case. You have a system in which pipe is very wide here. It's all filled with the fluid. Okay, it's all filled with the fluid. And clearly, as it's flowing, your sense will say that this around here, the speed will be less than over here, right? You probably have some experience in watching the river, and then when the river narrows, the stream pick up speed, right? When you constrain the river to flow in a very tight gorge or something, it just goes faster. So you may have seen that already. And we'll see that this comes directly as an implication of that. So let's see, over here the speed is V1, and this area of cross section here is A1. Okay, so we want to compare with what will happen over here. Let's see, speed is V2 and area of cross section is A2. Well, so over here you can see that let's look at what will happen in delta T. Delta T in time delta T. Well, this is saying that maybe I should put it like this. Okay, this much, if this is V1 delta T, so all of this fluid, right, would have entered into this space. And over here, let's keep it same. V2 delta T, all of this fluid would have moved out, right? Because between here, between point 1, this point, and this point, any fluid that comes in must leave because this guy's volume is not changing. Between here and here, these 2 points, all the fluid, this volume is fixed. I want you to think about it. This is a very important point. So let's see. So this volume the volume that came in 1 second must equal the volume that left in 1 second. Or volume that came in delta T must leave in delta T. So how much volume came in? Well, we have A1 V1 is the rate which the volume coming in times delta T. That's came in must equal to A2 V2 times delta T. This is out. So delta T cancels out, and I got this sometimes called equation of continuity. It's A1 V1 equals A2 V2. So this it directly implies that if I have a pipe with area of cross section is same, I'm not saying that this thing is kind of has another pipe coming out, and just it's the same pipe. It's the same pipe, right? I have same pipe in which the water is flowing. Then you have A1 V1 equals to A2 V2. Actually, if I look at this, if the area of cross section is bigger, if A is bigger, then V will be smaller, right? So that this just means A bigger means V is smaller. Wherever A is bigger, V has to be smaller because their product has to be equal throughout in the same pipe. I want to have another example of this, so I just pause and I will restart after pausing. Now let's look at a system. For instance, you may have a apartment building, and this may be one apartment, this may be another apartment, and this is a common supply, and both of them are on at the same time. These things are on the same time, and this supply is on all the time. All right. So I just showed two, maybe a whole bunch of branches, but let's see, there's only 2 branches here. What do you think will be relation between these based on this idea of a continuity, and why that would be the case? I'll let you think about it a little bit, and I'll come to you. You can pause the video and see if you can think on your own. Okay. All right. So what I want is incompressibility, right? Incompressibility. I want to apply this idea of incompressibility. It means volume between here, and here. This volume cannot change. So whatever, all the fluid that are there, they cannot change. That means anything that's coming in, anything that comes in must equal to anything that goes out. Sum of all the things that go out. So amount that comes in is A1 V1 delta T. Say during delta T. So that's many volume. That means liters came in this amount of time. So the unit of this guy is, say, meter cube over second, and this guy is second. So that many meter cube came in. Well, how much went out? Well, this time went out through this and that together, right? So A2 V2 delta T plus A3 V3 delta T. And this has to equal to that because what came in must have left. Because this cannot change. The volume can, because of this incompressibility. So I got A1 V1 delta T equals A2 V2 delta T plus A3 V3 delta T. Of course, delta T was arbitrary time I picked to look at. So rate at which, this is the rate at which the fluid is coming in must equal to the total rate at which fluid is leaving. So I get A1 V1 equals A2 V2 plus A3 V3. And this happened because it was coming in just one place and it's leaving at two places. You can reverse the arrows. You can say, hey, what will happen to if I had two sources, two pipes, and they're coming together, it's coming from here and here, but it was leaving over here, right? And same logic you can apply. So there will be two terms that's coming in must be equal to one term that's leaving, all right? Okay, just to recap, we have a important measure of flow rate of fluid. So this is volume flow rate, and that depends on how wide the pipe is and also how fast it's on average flowing. So this is called average speed of fluid. And if I apply it to the same pipe, but at maybe two different places, the pipe may be changing in how thick the pipes are at different places. If that's the case, then I get what is called equation of continuity. There is you will find that there's also an interest in what's called mass rate of flow, which we now discuss, okay? So mass rate of flow. As the name implies, it's kind of the same thing as volume, except instead of looking at how much volume the fluid is flowing, I want to account for flow based on how much mass of the fluid is flowing. And obviously, if I take a volume rate and multiply by the density, I'm going to convert the whole thing into the mass flow rate, right? So if I take a Q and I just multiply by density, right? So I take a density rho. If I multiply, this is meter cube over second, and this is kilogram over meter cube. So you can see it in the units, it's going to work out mass rate of flow, mass per unit time, right? So this is sometimes called current. So this is we can denote by I, letter I, which can be confusing because we've used letter I for moment of inertia and other things. But this is later on when you do a study of electricity and magnetism, this will be kind of called electric current. So there, instead of mass rate, you can say charge rate of flow. That will be current, electric current. Mass rate of flow is simply called mass current or current. Another thing that you might encounter sometime is from this, you can see that if I write a little bit of detail, it's going to be rho A V. So if I divide by this area of cross section, it has a so if the whole thing is flowing, right? So it has a this says over the whole area, but sometimes I want to know per unit of this area, per unit area of the cross section, and that's called current density. So if I take this I So if I have a so-called current density, so how much of this current, how much of this mass current is happening per unit area? Okay, so there's another letter for that. That's J we use. This current density is how much current per unit area. So this is rho times V. So if I had an area of cross section, and maybe say this is the part, this is the real thing, right? In the middle is going to flow with higher speed. Over here is going to be less speed. Over here is going to be even less, less. So usually the speed actually is greater as a square if I had a cylindrical pipe, then the speed in the middle is highest, and a little bit later is kind of less, and then less and less and less. So that's the profile. It's called velocity profile. And so if I look at this guy, it says, you know what, J here is the highest, max. So at this point J is max, this point J is less, J is even less, and J here is 0. So over the cross section, J is actually varying. So J is a function of where I am on the cross section. So J can be a function. J can vary over the cross section. If you later on, I'm going to do for the calculus people a video how to use this varying J. But for non-calculus, sometimes you might encounter just definitions like this for for just having more terms. But if it's not varying, if it's not varying over the cross section, there is no need to go over into the calculus and have more difficult techniques. If J is constant, we just J is constant. That makes a J times area being current, and you really don't get anything out of it. You just learn one more term. But then most of the physics, most of the problems, and most of the situations you can encounter just require you to use these two equations. I will recommend paying attention to this and these, and memorizing these equations and practicing, making sure you understand physically what's going on. Narrow pipe, wide pipe, higher speed, low speed. Okay, so I will see you in another video.